Hello and welcome back to ST118 Statistics and Applications, Session 8. In this video, I'd like to explore the applications and use of non-linear regression. Okay, let's start with that title, non-linear regression. So if I run out of space, allow me to just write NLR, right? Okay, so nonlinear regression. Why nonlinear regression? So I'd like to start by talking about the applications, right, and usage, and also the types that come along with what we want to do today. Now, nonlinear models means anything but linear, and that means that includes everything in the world of mathematics, everything, right? So that's why it will be a very huge topic, and we're not going to uh, discuss everything, and we'll focus mainly on how to connect you, the student, the reader, the audience, with the use of nonlinear regression. Now, because our techniques to do nonlinear regression, number one, they are naturally going to be much more mathematically involved. Number two, however, there's always a however, not a but. However, most of these difficult mathematics, they are already embedded, fine-tuned, tested, right, and highly respectable, reputable libraries in Python, in R, even in Excel. And so you can just run a function and be able to solve it. Right? And we talk about what is solving. So the models that we want to talk about, they would be polynomial models, power index models, and exponential models. Okay, so these are very, very frequently encountered in daily lives, in businesses, finance, accounting, social, how do you call it? Social encounters and measures, environment, and that's why we want to kind of know them a little bit more, rather. And of course, there's another very important model, and that's called the logistic regression model, which has nothing to do with the logistics with the S behind, right? It has no S. It's just named logistic. More to do with logarithm, I would say, than the logistical movement of goods, right? So nothing to do with those movements and stuff, just logistic regression. And we'll have a look at this very interesting regression model, both interesting both because mathematically it is interesting, but I'm sure you are less excited by that. But also it applies to real life situations a lot, and yet we cannot use our tricks, our ways to find and solve polynomial power index exponential models. Cannot use that same method to solve logistic regression models. So we just want to talk about that. Okay, and yeah, that's pretty much our agenda, and then perhaps I'll just show you a short example, numerical example. Okay, so let's talk about the application usages, right? So the applications are really a lot more important for you guys to acquire, to associate, that is all. So that you know that you are supposed to be using polynomial regression, power index regression, exponential regression, logistic regression. You know why you are using it. You know that you have chosen the right model to do it. And then how do you know it is the right model, right? That's why you need to have some sort of a acquisition with how the connection is, right, between the chosen model and the real world. Sometimes it is clear, but other times you have a choice. So in other words, no one is sure about your situation. You just have to try them out, right? But holding the attitude that, oh, well, no matter what, I'll just run all the models and then choose the one that is so-called having the smallest p-value or whatnot, that is not going to work, because that is like a little bit blind to the signals, right? The information coming from your context, your environment, your situation, your particular situation that the sample data describes. So on one hand, we have all these models available to us. We could try them all. And on the other hand, after you try them all, you are also not sure why you have to pick one of them, or why you pick the smallest p-value when the p-values computed are not in the same context, same model, same regression model, right? Same sequence of calculations. So the p-values are hardly comparable, because p-value is a probability, which is count of event over count of universal set. So the count of universal set is not the same, right, in all the four models. So you could hardly try to compare the p-value. So there's no reason for you to use the p-value to say, oh, because exponential has the smallest p-value, we use that. Right. So let's just quickly look at, first of all, why nonlinear, right? So I did say, of course, you are now checking back my previous video in session 7 about everything about linear regression. And I did say that linear regression, even though it's linear and very limited in some sense, right, only by line or hyperplanes, right, so it's very structured, very monotonous, right, just no feature, nothing, just a line or a plane. And I was trying to convince you that that's enough, right, because even if real life measurements, right, they curve, they have waves, they change in a nonlinear way. When we so let me just say that why linear, right? So when you limit the interval, for example, the x1 or the x2, you limit those intervals to very small range. Small is relative, right? Like 1 million to 2 million can be small relative to 1 billion, right? So we're just limited to this range of wealth holders. Okay, so this range, right? We're not talking about the so-called ultra rich, right? So don't include them, just to get this. So when we range it in a relative context, then it could still be linear, right? So for example, if we limit the interval, right? So we were saying that why linear? Because if the x1 or the xk compared to y, right? So if the actual is like that, right? And this is a wide range, we can limit ourselves to short range here. And this part is linear, right? Limit our regression range to short intervals. So then we can use linear regression, and it'll be still a very good model to predict, to investigate, to explore, right? The issue is why non-linear, right? So now then, why non-linear? So am I not like contradicting myself? Huh? So why non-linear? Well, non-linear because a few things, right? That the rate of change is very high. So the y changes rapidly, either with x1 or with all the x's, right? With xi. Doesn't matter. Even if one of which, you will not get a very linear kind of result, right? And it may be that uh, reliable, accurate prediction uh, is important in the context. Okay, maybe it's about drug efficacy. Maybe it's about financial returns. You want a more accurate kind of model. You don't want to approximate. Approximation is not acceptable. Okay, and another point is that short interval, because we truncated it, right, doesn't make sense. In the context. So in the situation that you are in, so maybe you are now the senior VP of wealth management, and you have to look at all the entire customer profile segments, including those that so wealthy, medium wealthy, so 1 to 2 million range, 2 to $50 million range of investable assets, then 50 million to 100 million range, 100 million to $1 billion range, something like that. Okay, so so you're looking at these four customer segments and their risk appetite, the expected returns, their intended goals, the time of investments, everything is different more or less in these four segments. Okay. So you say, okay, you are the senior VP and you say, okay, let's limit the range because I did study Chinchika's ST118, and I know that I should segment it so that I can apply linear regression, right? But then that doesn't give you the complete picture. And combining four results, four models for you to investigate also will be a little bit tough, right? And so you have to, so short interval doesn't make sense. You really have to include the whole interval, yeah? And when you include whole interval, but then for large interval, right? More variables, more latent variables may come in, may influence what? Right? So the latent variables will be environmental and not captured in any of your x1 to xk. So you are talking about, okay, the family, married or not, have how many children, income level, so you want to learn about that person or the company. Let's say person, you're just dealing with personal wealth management. So income of the person and so on and so forth, right? So when you're talking about people with large, huge income, then some other variables may come in. They may have increased level of expenses, luxurious taste, things that they like, right? That are very different in the price range than others. For example, ultra wealthy people may now access certain hobbies, such as, okay, don't think wrongly, hobbies as in, for example, owning a soccer team, all right, owning a racehorse, which takes a lot of money to feed, right, and to train and to upkeep the health and so on, plus the horse racer, right? So these are not hobbies that can be acquired by or taken up by mid to lower segments of customers. So they have increased expenses and all that stuff. How much proportion of their wealth is being affected, and so on and so forth, right? So other variables start to kick in when you extend, and so the extended profile may then look different, right? It may look like that, right? So the extended profile, because new latent variables kick in, latent forces that you didn't know about after certain intervals. Okay, so the extended range for x1 will trigger those. So it's like, for example, also let's predict. Okay, let's run a model to predict Singapore's GDP for next year and next year, right? So using past 5 year, 10 year data. So we can try to do that for immediate future. But if we try to use the model to predict GDP for Singapore 10 years down, 20 years down, 30 years down, why would we want to do that? Oh, because of climate change, right? We need to see if our GDP can afford us to build say, the coastal barrier, right? To at least, from the geological perspective, tentatively, for several decades, perhaps it's tentative, to block the rising tides, right? So maybe going from 0.5 meters to 1 to 1.5 to 2 meters, right? So we try. Okay, so building that, we know how much it will cost, and do we have the income, the GDP, to sustain that? So we try to project. Now, when you try to do that as a regression model, 10, 20, 30 years down, then some latent variables come in right now. Yeah. So for the next 5 years, we for forecasting, predicting GDP, modeling GDP for 1, 2 years, we can probably assume interest is about the same, right? Plus minus a little bit, but wouldn't affect GDP. We can assume that maybe political parties, political climate, political volatility is about the same, right? So wouldn't change too much. We can assume that generally, right, most things are stable as is, right? We wouldn't imagine very drastic changes. But 10, 20 years, 30 years down, would you say the same? Inflation effects start to kick in, right? Already, some of us already have felt that change before and after COVID-19, right? So that is already one such, but that's externality. So externality can come in. Rare but impactful events are what economists will say as externality. So COVID-19, right? Lehman Brothers financial meltdown, that was another one, right? In the way that's man-made, right? But then COVID-19 can come in. Would meteorites strike any part of Earth, that would shake the entire world's finance, right? So again, it will affect everybody. So, and I don't want to talk about other man-made disasters. So a lot more variables will come in. Inflation will come in. Population migration, the impact of that may come in. Singapore may start to attract more people to now become, instead of 6 million people, becoming 10 million people, right? So who knows? And uh, Singapore's land may expand a little bit more, right? Landfill, because it takes time, right? So various forces that act slowly or cumulatively over time, if you're trying to model it short intervals, or it may not be very serious if you ignore those, like holding all variable constants, right? Ceteris paribus, hold everything constant, don't worry about that. We know that society is moving, people are migrating and coming in, but don't worry about that, because you're talking about overall big GDP number, so don't worry about that. But 10, 20, 30 years time, we won't know, right? Would Singapore's GDP continue its growth every year, 2%, 1.5%, or would it start to decline? We better be wary of that possibility too. Will it become a minus 0.5 for a few years and then minus 1% for another few years? We better never, right, let that happen. But then that's the whole point of this long-term planning exercise. And what I'm saying is, you don't know what are the forces that come in, right? Because your current x1 to xk didn't capture them. We're not worrying about them, right? But they will be the main worries when your interval gets larger, and it becomes then non-linear. No matter how linear you want to talk about it, it becomes non-linear. So for many reasons, we still need to sharpen our skills to take into account the non-linear kind of situations. All right. Now, I did say about all these things, and even if you don't extend for large intervals, y itself, that means the costly, expensive, rare event variable that you are measuring may still change rapidly. Think of acceleration causing the change in speed and so the distance becoming quadratic or non-linear. Think of that. There is the force, right? Because in physics, force leads to acceleration. Acceleration causes the distance versus time. So if distance is your y, the time is your x, then initially at constant speed, zero acceleration, distance covered is proportional to time. You just wait longer, you get proportionately more distance covered. But then if acceleration, that force is in existence, but you didn't know, right? Because it's not in your y, your x. Your x is the time, right? You didn't capture that acceleration. Then what happens is you will observe that it starts to grow, right? This curve is not always exponential, right? But it's more parabolic. That means square. Distance will be covered proportionately to the square of the time involved. You wait for 2 seconds, you get 4 meters covered. You wait for 8 seconds, you get a square of 8, so 64 meters covered. So that kind of behavior will not be easily approximated by a curve, by a line. So you cannot like shorten the interval, right? So give an example in real life. We would like to study the engine behavior of sports cars in order to win F1, right? Singapore is also hosting F1. So we like to ensure Mercedes or Ferrari or BMW, right? So their engines are, doing well. But how do we know, right? Because after complicated steps of manufacturing, does the engine behave the way you have designed it? So a lot of things are at work, right? The precision of the engine shape and engravings and whatnot, right? The tolerance of the temperature, the ability of the engine to keep the same shape, right? While at high temperature of ignition or whatnot. So all this stuff, I don't know, right? I'm just saying what I think might be applicable and already is scary, right? A lot of things are involved. There is heat, there's mechanical energy, right? There is combustion, the chemical effect, there is electricity, right? Will electricity lead to the combustion being higher, faster, or slower? How about the exhaust, right? So all these stuff, they are happening in split seconds. And what we want is to win the race, right? So we want to measure, right? We want to measure the distance covered, right? Or even for that matter, so the distance covered by timing, by timing. So in that case, you can understand, right? So that the engine may having the acceleration may cover distance this way, right? And then because of changing gear, it drops a bit and then goes up. It may cover this way. At first, it's a bit sluggish. Turns out that the engine maybe at first a bit sluggish, then change gear a bit, then becomes very fast. Second gear is very good, but third gear not so. First gear very bad, right? So only with data and measurements, then we can start to find out the produced engine because they'll be custom made, right? So produced engine, is it performing to our effect? Engineer can say what they want. Designer can say what they want. Yeah, my design is the best. Engineer can say, yeah, it was crafted everything nicely. But production side had some issues, right? Then end up this engine may not work. So we want to test. So when we test, we realize, hey, the curve comes out, right? So all these things will then be able to come out only nicely or described by a non-linear curve, right? So again, y changes rapidly due to acceleration. Now, I use car because definitely they are affected by acceleration. But there are also economic accelerations, such as government reducing tax. That's like boom, right? That's like a economic acceleration, right? That's the whole point. Maybe that's why government initially thought about reducing tax to boost the economic activity, right? Yeah. So there are such forces as well, right? And financially, right, finance circle, same thing. Reduction of interest rates. The Fed just announced reduce interest rates, for example. So they have a meeting. They say, okay, reduce not by zero point 0.5 percentage point, but directly 1 percentage point reduction. Wow, extraordinary! It never happened before, right? Suddenly, there's a big, huge acceleration of financial markets performance, right? And then, of course, subsequently, because that's not the goal of the purpose of reducing interest rates, right? And then subsequently, it should percolate down to higher economic activity. It should, doesn't mean it will, right? So the whole goal and the plan for the reduction of interest rates is to give an acceleration to economic activities. So I hope by now you are convinced or over convinced, right? So let's look at some of the application areas one at a time, perhaps. It would be good for me to first list out what I mean by polynomial power index. So a polynomial model would look like something like, I will use back the b suffix, b0, b1 as the coefficients, right? So there'll be, and I will only use one variable, okay? So let me write that down first. So it'll be y is equal to b0 plus b1x1 plus, and because I will only use one variable, I won't use x1, I just use x. Just so as not to make it so confusing. So let's understand one variable first. And already it's more than linearity, because we don't stop there. We stop at another b2 x squared. Okay, plus and so on, plus until b k x to the power of k. Up to you. Okay, so up to you. So it's always x squared, x cubed, x fourth, x fifth, x to the power of k. But the coefficients, again, just like linear regression, they are left for us to determine. Okay. Next is power index. Power index model basically means that x sits on the floor and we don't know about the power. So the power is over here. Okay. So if b1 turns out, because remember, just like linear regression, we're trying to determine b0 and b1. If b1 turns out to be 1.99 or 2.01, which is approximately 2 in all practical purposes, then we have a square or parabolic relationship between y and x. Right now, yeah. So we have then determined that, oh, basically y is like the area of x. Knowing the length, we can tell the area by our model. But if b1 were to be hovering around 0.495, 0.501, right, it just means that y is proportionate to the square root of x, because x to the power of 0.5 is also square root of x. So it would mean that, oh, actually now we captured x like an area and y is like the parent, one side of the squared parameter. In fact, x will be a squared area, has to be a squared area. Then we take the square root, y is like the length of one side of the squared area. Right, we can think of it that way. Other values of b1 will then reveal other relationships. Right? It could be 0.3333, right? 0.1 and so on so forth. Right? But again, that would be why we want to review REVEAL, review, show the actual values of b0, b1 so that we can understand the relationships between x and y a lot better. And of course, finally, the very catchy term, exponential model, captures the situation when y is equal to b0. This time round, x goes to the index, right? And is accompanied by possibly another constant, which can be, of course, 1. And if it is 1, b1 is 1, then it disappears. So we like to know if b1 is negative, right, or positive. If it's negative, then it's a decaying process. It's exponentially decaying. The larger the x, the smaller the y. In fact, so small that it may go to 0. Hopefully, right, it is something like some sort of cancer drug. If it's effective, then as we take more and more of cumulatively, more and more either number of pills or milligrams of that drug, the cancer cells found per mole of blood drops will be reduced exponentially. So the cancer cells are dying in a very rapid way, right? So exponentially disappearing. They have no chance to reproduce, and that's why the patient will be healed, right? So that's good. The opposite way is the spreading, right? Spreading of the cancer cell. Huh? So that's when B1 is positive, and then the magnitude of B1. If B1 is positive but small, for example, 0.012. Okay, so let's say we obtain data from cancer patients, right, and found that as time passes, this newly discovered cancer, right, exists in the bloodstream, and grows, right, but then very mildly, like, X may have to increase by 1 year for the growth to increase by another 10%, or 5%, or 2%. Then in that case, maybe the doctor says, you know what, sorry to say you have that kind of cancer, but fortunately, this kind of cancer is really very mild. You may also choose not to do anything about it, but just keep monitoring, something like that. Huh? So at least we are not so alarmed by this discovery of this type of so-called weak cancer in this patient's body, right? Something like that. So the B1 will be very, very important telltale sign. Just like in linear regression, our coefficients starting from B1 onwards, those coefficients that are kind of connected to the variables, right? The x1, x2, x3, like all these cases. So from B1 onwards. The B0, all right, in the power index and exponential cases, they may indicate some sort of connection to the real world. Sometimes in the decaying case, perhaps it might be the largest quantity of cancer cells. So it's like B0 is the largest amount, but decaying by how much, that kind of thing. So it's useful information, but not that critical in terms of decision and impact. So again, B1s, all the coefficients, all the gradients play a big role. Okay, so and then of course we have the logistic model, right? So which looks different, and I want to talk about logistic regression later, not here. Now, why I put them together is because they are going to be mathematically dealt with. What's dealt with? Dealt with means to find the coefficients of these unknowns. Once we found it, the model is completely determined, right? So mathematically, to so-called solve it or to find the model means to find these coefficients. The procedure to do that is to just make use of linear regression, which I'll talk about in a while. But let me finish up with the applications first, right? Why I want to write them out first is just so that you have the structure in your view. You know what I'm trying to say. So, okay. Now, first, let's talk about the applications for polynomial model. Right? So, polynomial model, we may have, for example, A. Right? We may have revenue being approximated by B0 plus B1 price plus B2 price squared. Right? More because when we have squares and above, the curves can start to change, can start to have turning points. That's what we are saying. Can start to change its mind. Right. So if we have P here and R here, so as we increase the price, our revenue should increase. Right. As we increase the price, our revenue should increase initially. So if we have been selling $1 and selling 100 units, then we get $100. $1.10, we should get $110, right? So it kind of increases proportionally. But that is still within the inventory of dollars and monies in most people's spending budget pocket, right? When you increase from $1 to $10, you may start to have people who don't agree to your price. What? So expensive and yet it's not even a luxury good or whatnot, right? Even if you're a luxury good, I'm not going to buy because I want to buy budget good. So then in this case, you are in for a turn. So that's it. You're in for a turn. That's why we need the turn. We need to see if the turn exists by collecting data. If the turn is sharp, right? Is it going to fall like a cliff? If the turn is going to be shallow, it might mean we have overpriced ourselves a little bit. Let's correct ourselves. If it's sharp, means we have gone beyond our profile, our customer profile, kind of maximum budget, right? So they totally avoid us. Most of them totally avoid us. We don't know. I'm just trying to kind of like come up with a feasible explanation for that observation. But you will see why, right? There's a turn, right? So the thing is that we would want the square to be sitting inside. Then if we have cube, the cubic polynomial may also curve downwards, but going further, it will go upwards, right? So, but then we may only capture this part of the. So we can also try using cubic polynomial, right? Cubic polynomial will go this way, and if you extend x even further, it will turn upwards, which is making no sense, right, in real life. But as far as this part of the cubic goes, it will be doing quite okay. But then, of course, we will see that the B3 could be a 0.0001 coefficient value times x cubed, which means that the x cubed is really not playing a role, right? So no point using the cubic term in that sense. Okay. So let me just quickly move on to another example, which is the use of advertising. Okay, the sales is equal to B0 plus B1, let's say advertisement budget, plus B2 ad squared. So same thing, the kind of sales that we get could be described, right? Could be described as point of diminishing return. So past the point of diminishing return. Diminishing return, right? So when we have increased budget of advertisement, our sales go up. Even if you don't have advertisement, there's some sales, not zero sales. Okay, so when you have more advertisements, it will peak out, let's say, at certain point, right? There's still increase in sales, but just that it starts to be not so efficient. You are increasing advertisement by twice, the sales increases by 10%, that kind of meaning. All right, so we typically call that the point of diminishing return. And once we have a data this way and we can fit the a portion of the parabola, right? The parabola is very nice curve because it has all kinds of curves. It has a rather straight line portion as it climbs. It has a steeply curving part as it navigates around the U shape, right? The peak. Then there is the peak itself, which is mostly quite useful to talk about some change of mind, right? Like the revenue case. And for the downward slope, it also shows matches very well with some data behavior in real life. But the point of diminishing return is very well approximated by the just before the peak part, right, and then extending downwards. So at first, great increase in the sales, then after that, diminishing return, right? Next, I can think about the cost, production costs, production cost curves. Right. So again, the cost could be approximated by B0 plus production quantity, right, times B1 plus quantity squared times B2. Why? Well, depending on which factory you are from, but there are factory lines where the quantity and the cost in the sense of variable cost, right? At first, there's a cost, right? Fixed cost. Even if you don't produce, you have a fixed cost, and the so-called amortized fixed cost into the variable cost, right? So the cost initially decreases with efficiency, right? As you increase the volume, the the unit cost tends to decrease, right? Because you are able to so-called take into account the production efficiencies. Same machine that I bought, I produce 1 million unit, of course, is far better. I get more returns, lower cost per unit produced than producing 10,000 units, right? So, but then after a while, if you have to go into overproduction mode, maybe the machine starts to need excessive maintenance, right? Then the cost may increase again. Right? Or you may have to hire more shifts of workers in order to produce the extra 100,000 units, which is 1/10 of your 1 million units. So the 1 million units perhaps is the sweet spot, so to speak. Then you get more orders, right? Then you increase the production by 10%. But then because of that, you need to hire overtime. And hire overtime, you either hire or don't hire. You cannot hire today. Okay, so it depends on the employer, right? You let's say the normal case, we hire the overtime shift. We pay them whole 8 hours of shift time, right? Because you have to ensure some fairness to them, right? Rather than hourly pay. So if we pay them whole 8 hours of shift time, but then just to produce the 10% more, right, in quantity, right? End up our cost per unit sales, per unit production will start to rise. So it may rise and then after that taper down again. I don't know. But at least for this part of the quantity of production, for now in my factory, in this production line, hey, we are experiencing this weird U-shaped phenomenon, right? So best described by a polynomial curve, right? Because if you invert this, meaning the B2 should have a positive number, then you have a bowl shape. The U shape is facing up to describe this. But what is the exact value, magnitude of B2? That's what we are interested to find out using the data. Okay. Others could include asset depreciation, or for that matter, appreciation. Right? Appreciation or depreciation with time, right? So you can have asset is B0 plus B1T plus B2T2. Now you see that this equation or this model is really very similar. In fact, it's the same as the model for distance equals to initial distance plus, right, the some coefficient times time square, right? So distance covered under the presence of, what do you call that? Under the presence of acceleration. So that means, hey, your asset is being boosted, right? You have positioned your asset or you have bought the correct type of asset, is being boosted, right? So basically, it would look like, I'm trying to squeeze in here, it would look like, but you just need to know the shape, right? So some sort of distance traveled, but here we have asset value is going to go upwards as time increases. That's the appreciation, right? And of course, you have some initial principal purchase value. As time passes, B2 is negative. As time passes, it depreciates very quickly. So it's a bit like mobile phones, right? Wow, when you bought Apple, $1,000. Okay, maybe Apple may depreciate lesser, right, than Android phones. When you bought it, $300, then over time it depreciates very rapidly because 6 months later new models come out. The previous model that you bought as new halves the price or drops to only 60%, maybe not halves but 60% of the price, right? Then after that 40% of the price, then after that, so it's never going to be $0. Well, should I not say that, but it's going to keep dropping, right, at different rates, maybe after a while it becomes antique, like my Nokia phone now, right? It becomes antique, and if I sell it, maybe I can get more than the worth of my phone. Probably not, but it's not going to be $0. And another interesting example, perhaps, is customer customer satisfaction versus waiting. Does that make sense? Um, customer satisfaction is going to be modeled by B0, B1 plus waiting time W, B2 waiting time squared. Why do we need square, right? Well, we want the drop, the beyond the peak drop. So let me just park it here because you just need to see the shape to link with what I'm talking about. So I make customer wait what will happen to their satisfaction level. That's the relationship we are trying to study here, right? So over here, initially, if I make them wait a little bit, they would be not happy, right? But then the unhappiness will not be so drastic, right? So it's like you order a chicken rice, you have to wait for 3 minutes, 4 minutes. I think you would find it reasonable, right? You won't say, I want chicken rice now, then 10 seconds later, where is my chicken rice? You also won't behave like that. So, at first, there is some sort of a drop, right? So, infinitesimally, very, very small. There's a drop. And then after that, beyond certain timing, right, they drop drastically. Like, not reasonable, right? So, very bad. This will become very impatient after some time. So we like to know what is this after some time. So we like to know this knee part. What is the waiting time for this knee part of the curve, right? So instead of diminishing return, it's like a trigger point for a collapse in the customer satisfaction. Okay, typically we get the customer satisfaction level by some sort of Likert scale, 1 to 5, right? Um, Perhaps at that range, right, we can do a curve-like thing, right? So this is 1 to 5. We allow for 2.2, 2.3, 2.4, 3.1, 3.2. We allow for that tentatively because like a scale, you can compare. 5 is a lot better than 4, right? 4 is better than 3 and so on. So likewise, we can interpolate the values. They don't exist in the data, but we can allow that to happen because those interpolated values are still comparable. So it is helpful towards our curving, right? So the curve may produce customer satisfaction levels will reach 2.622, right? That kind of theoretical value, but so it doesn't exist in real life. But then we can interpret it. We can kind of say 2.62. Okay, fine, we can live with that. Or that's bad. It's still below 3, right? So we can interpret and then take action. So best part is also we find out where is the knee, right? The turning point, the so-called too steep for us to absorb point. And of course, that also is subjective to our own interpretation. If it's a company, if it's an organization, they can then examine what is acceptable to them. We better shorten our waiting time. But then look, to produce that service, to produce that effect, to finish that transaction, we need at least this amount of time. Because if we, you know, pressure our cashier, imagining if it's a bank transaction or something, if we pressure our cashier officers, our customer relationship officers too much, then they may do a sloppy work, right? They may hush off the customer. Hey, so are you done or not? So if we do that, then it may not be too good because they will rush off this customer in order not to let the next customer wait for too long, right? So that would have a chain effect. So they will discuss and then they will interpret. So this kind of model will be super helpful. And who doesn't have customer, right, for businesses? And so there you go. Okay. And next, I like to talk about the. Let me find the parking lot first. The power index models, right? So power index models. Yeah, maybe this will be a good place here, just at the bottom, since they're all somewhat related, right? All related to application. Okay, so let's talk about the power index model. Okay, and a quick reminder, power index model looks like this. And I only have one explanatory variable, right? So I will just call it x rather than x1. But if you have x1, x2, x3, that's fine. You can then experiment with either you multiply them together or you add them together, right? So that starts to get a lot more complicated, but we'll stick to that. Stick to a single one first, okay? Similarly, for the exponential case, right? So then here you want to experiment with if you have other factors. But because it's already non-linear, both mathematically and interpretation-wise, they are getting more complex. Now, the mathematical part has been overcome, so the software can easily deal with multiple variables and non-linear and all that stuff, no problem, right? So, but then it's ourselves, right? So, unless you are very strongly mathematically trained, to really get a deep insight easily from interpreting multiple non-linear regression results, it might take a little bit of brain damage, right? So just a little bit harder, just a little bit indirectly, yeah, and you have to imagine a little bit more with backed with good mathematical foundation. So let's study one variable at a time. That would be a safer bet. So that's what I'm trying to say here. Okay. Example A. Same idea, in some sense, economies of scale. Economies of scale. Right. We have economies of scale, right? So we have cost is equal to some sort of a B0 quantity raised to the power of B1. So this kind of curve, depending on B1, right? So if B1 is going to be positive, like maybe 2, then it's a square, right? Square, it will be behaving like a polynomial. It could be this, and if B0 is positive, then it's a positive U shape, a bowl shape. If B0 is negative, then it will be an inverted U-shaped curve, depending on the data that will drive the coefficients to the relevant sign and magnitude, right? So in the case when the cost is more than square, then by assuming that it is a square model, because we got to define the model first. So you already selected the quadratic model, then it will stay as quadratic, right? So then you got to try the cubic again, then you try the quartic again. What if it's not neither quadratic nor cubic, neither maximum 2 or maximum 3? What if it's 2.5 for your factory? Then neither the quadratic model or the cubic model will fit very well. But this will kind of like search for the correct power index. Search, I say search, right? So, but mathematically it's just calculated. But it will search for the, you can think of it like it will search for the correct and even very precise value, like 2.73442, power index. So if 2.7 and 2.0, 2.7 and 3.0, for a large B0, which will magnify, right? And your quantity is large. So raised to the power of 2 and raised to the power of 3 is a big deal of difference in the cost. Then 2.7 being a more accurate, at least more precise value, 2.7 is not 2, is not 3, right? Will help tremendously in knowing your cost performance, right? So that's why it is a good idea to find out. So here we can talk about cost curve, economies of scale, which means that for the quantity to increase, as quantity increases, the cost drops, right? At first steeply, and then after that, still dropping, but not much more. So if you are on the produce and then sell, hope to sell, so you produce first and then hope to sell. Then you wonder what's the right quantity for you to produce. Then you want to find that, again, sweet spot, right? What's the point of diminishing return, and then before which is the economies of scale, right? Something like that. Then we can talk about the distribution of company size or city population. So company size distribution. Like the phenomenon of company sizes in a city or in a country like Singapore, very small, right? A city country. Distribution of company sizes. It would be the case where the size, right, is related to the rank of the company in terms of whatever measure you want on the sizes. Typical measures might be number of employees. Okay, number of employees, the larger the company, right? So they're like, for example, hiring 100,000 workers and above. Okay, so goes to rank 1. 50,000 and above, and so on and so forth. You can also categorize or rank the companies by what? By rank the companies by their revenue, annual revenue, or their annual profits, right? Something like that. And so when you do that, then it starts to have some sort of again some sort of curve, a sort of declining curve, right? That rank one, like the sort of first prize, right, tends to be very large in the size. The count might be few, right? So for example, a few large companies, each one hiring 100,000, 200,000, 150,000 workers, could basically be hiring a lot of people of that town or that city already, but there's only two or three companies. So we're not talking about the count, huh? We're talking about the size of this measure that you are using. So it could be high, and then after that lower, and then lower, and then lower, but never quite zero right now. Yeah, never quite zero. So it is possibly not quadratic, because there's no theory that says the drop in company size has to be based on quadratic or cubic or for whatever reason. So that's why it might likely being a natural phenomenon, right, for any chosen city like LA, New York, Singapore, Tokyo, in that sense. Uh, for any chosen city, the size ranking, right, size versus ranking of companies, uh, employees and revenues and profits would be a natural phenomenon. And so that power index B1, which is tagged with a minus sign, so B1 is a positive number, is a number that is going to be close to 1, right? So if it's close to 1, then it's reciprocal. That means B0 divided by R, right? B0 divided by R. And so that's going to be basically a kind of phenomenon that would need the data to tell us what is the right number for B1. Okay, it can be a number that's 1.05, 1.08, slightly larger than 1, right? Or a number that is smaller than 1, so like 0.92, 0.88. Right? So it would change the curve in a way that would so-called best fit the data, right? So again, but our starting point should be that we know, right, the curve is not really a straight line in the first place, but tell me, right, using the power index model, tell me how it curves. Then we can talk about, say, in trading, right? So there is this idea of price impact. That means the change in prices versus large trades. So in this case, we have the change in price, right, is going to be modeled by some sort of a constant times the volume, how frequently, right, the volume of the trade. Okay, so the large trades, why would it affect? Why would it impact the stock market price versus the retailers? Retailers means you and I, one person's bank account. Even if you are ultra rich, very rich, okay, fine, maybe that's a different story. Then you might be one of those large trades, but I'm not, right? So in the small retail case, when you're buying shares, 100 shares, 10 shares, 1,000 shares, 10,000 shares, right? That's not large, and it won't impact the price too much or at all. But for institutional traders, bank traders, hedge fund traders, they will buy and sell millions of shares, and that's considered small quantities, right? So that when they do that, they have some sort of market moving ability, or the price, the asking price. If they're buying, they might shift the price up because they are generating demand. And if you are in the market at the same time with them, you're going to be chasing the same share item, that share that's available in the market at that point in time, you're chasing with them, right? So they would be able to gobble up a lot more quickly because they're offering high price. Oh, you also want, you also want, but I need them a lot more quickly now. I need to settle my customers' needs, right? So I don't mind buying 10 cents more, right? And that may be 5% more, right? So when you do that, when the hedge funds people and the you know large market participants, right, when they go in with large volume purchases, they will tend to affect the price more than, right, certainly more than the individual retailers, right? So that again is going to influence the price impact. That means the change in price. Then going forward, we have also, did we talk about that? I can say that it is the sales and advertisement, right? So sales and advertising, right? So marketing plus no, sorry, times marketing. So M raised to the power of B1. Okay. Okay. So let me just finish sketching the curve for volume. So large volume leads to delta P, not P, but delta P. So large volume leads to a big change in price, right? So something like that. And then for the diminishing return for marketing budget, right? So again, we have the more, right? The more, and if you market a lot, then you have diminishing effect. Like you increase the marketing budget, the sales kind of get stuck at some sort of a plateau. You increase some more, people get tired of it, right? So there is a kind of a rejection effect. Oh, I keep seeing McDonald's every 10 seconds. I'm like imagining burger in my mouth, chicken nuggets in my throat, and cheeseburger in my stomach. I'm like almost, I don't want to see this anymore, right? So if you overmarket, then after that you may see sales dropping. Some people react to this, but others don't. So you might see a drop, a little bit. But is it really drop a little bit or drop a lot? Right? How steep is the curve? We need um, the B1 to tell us, right? But this would be the case when we would then switch over to the polynomial side, because polynomial side can curve. The marketing side cannot curve. So if your data is this way, then unfortunately your curve will only go this way. Okay, so in this case, then we won't be able to see the we won't be able to account for any rejection due to over marketing. All right. So if this part is not there, and we use a model, we because of data scatter plot, we see that the data seems to be just curving upwards, right? Then this will be more like point of diminishing return, right? So point of diminishing returns. And so this has got a good contrast with the polynomial method. So polynomial method, you can have a curve. Even if at first you don't know, you see in the data there seems to be some sort of a curve, then it's good to use x squared, right, or x cubed, a curve to try to allow for that turn to occur, right? Then you fully allow the turn to occur. Whereas for the case of this power index model, it's if you imagine B1 is a square, right? Then basically it's like sales equals to 2 times m squared, right? 2 times m squared always will start from 0 and then grow upwards. It will then grow upwards, right? And it will not have a chance to turn because the turn is at 0. So that's why if you choose this model, then you only want to know the sort of rate of curving and not to have a U-turn, a change in direction. Whereas the full polynomial version will allow for that to happen. My last example will be talking about curve is the learning curve. So learning curve, learning curve versus labor. That means manual work, productivity. Manual work. It has to be manual. So sort of like saying that the time needed to produce the nth unit. Nth unit means many, many units later, well, will be some sort of a b0 times nth unit raised to the power of negative b1. b1 being a positive number. Okay, so the larger the b1, the shorter the tn, right? The smaller the tn, meaning the more experienced or the quick learner the person is in uh, producing the nth item. So if you imagine crafts work, right, or for that matter, it can also be classroom learning, the learning curve of a person, right? So the learning curve of a student, n versus t, the time to solve a problem. So let's say you're learning non-linear regression now, right? So if I give a quiz, one question, solve this non-linear model example, right? And it's the same question. And because all of you are online learners, you are independent of each other, I would assume air gap, right? Air gap, so is statistical independence. The time to solve the problem, if you're solving this the first time, okay, would be high. If after a few minutes later, I give you another problem, the time to solve that problem you have experienced already, so you know where to quickly read the numbers, but you're still a bit rusty, not very sure about things, so a bit of improvement, right? So it takes slightly lesser time. The first one you take 10 minutes, second one you may take 9 and a half. Different people will take different minutes, right? So there's a spread here, there's a spread here. Then the third one, right, occasionally a bit shorter in timing. The fourth one, shorter, and you get the idea, right? So by the time you solve the 10th question, you are so expert already. And let's say I don't change the question too much, right? So, and then you are very expert, you know what to do with the software, with whatever, and then you just respond in a minute, right? So that will be very expert kind of level. Time to solve the 10th problem, right? It will be very much lower than the time taken to solve the first question, right? That's the kind of learning curve, right? So there's a learning curve. That's why we call it the learning curve, right? So time to solve means you have fully mastered and you are an expert in solving this kind of problem. Yeah. Okay. So that is for power index. And unfortunately, I moved into the exponential territory already. So exponential models, what are they used for? They are also curves. And we have seen some of these like almost like an exponential decay. It's very small here, but the exponential curves, they are, allow me to use the word, more curved than power index curves, right? So they can be made steeper. They can also have shallow exponential, right? So it's like fat exponential, right? Taking a long time to diminish. Or think of maybe charcoal. right? Charcoal fire, right? So it burns and taking a long, long time to eventually die off until perhaps, let's say, we check using infrared optical sensors to check the temperature, right? Uh, Currently, temperature is 200 degrees, then half an hour later is 150. Half an hour later is 120. And so it just takes this long, long time to finally, extinguish the last flame and then slowly cools down. It just takes a long, long time. And that's why we like charcoal, right? Because the heat is being kept there, right? So that is the slow exponential kind of situation. And oftentimes, people might be confused with is it power index or should it be exponential? But for the so-called link in real life, back to which one should I choose? Should I choose exponential or power index? Right. Exponential looks like this. Power index looks like this. Difference, the x variable that you measure, one sits in the air for exponential. So that's why sky is the limit. It grows exponentially. We use this term as well. It grows exponentially. It explodes. We use terms like that. Explosion is also a chemical reaction that is essentially exponential in nature. Nothing to do with the rhyme of explode and exponential, but it's almost like exponential. But it is because 1 is to 2, 2 is to 4, 4 is to 8, that kind of phenomenon. So every time you have that kind of description, right, people say that it is exponential in nature, it is growing exponentially, right, and all that stuff. Essentially, that's like explosive growth. That's exponential in nature. Other times, power index will be like, it looks like it's growing rapidly, not linear, right? But we hesitate to use the word explosive growth to talk about that. Then likely it is an in between, and power index is an in between. So that's something to consider, right? Which model you should be using. Um, and because everything is b0 to the power of b1, e to the power of b1x. So essentially, uh, all these models will look the same. But I like to talk about the compound interest, right? Compound interest essentially is explosive growth in your money. That's why you should be saving right now, immediately, right? So it will be your your amount of money, which is equal to the principal, right? Uh, Approximated by exponential. And you don't have to worry about what if it is not E. E is the number 2.718281828, fixed constant in the universe, right? You don't have to worry about what if the exact form, the exact number should be 2.3, right? What if it is 1.5, right? Don't have to worry. So long as it is fitting the description that it is a constant raised to the power of x, raised to the power of some sort of x, the rate, for example, with time. Okay, so this is our b0. This is our b1, right? And essentially, we are talking about your money worthing. As time passes, your money grows explosively, and at time 0, you have principal amount, and then it grows explosively depending, right, on the rate. The higher the rate, the more, the steeper, right, the quicker it blows to infinity. It will go to infinity much more quickly than power index mode with the positive index. So if they are racing to the sky and universe, exponential model will go there much more quickly, right, without any fight, definitely. So that would be one case. Second case is, of course, user growth for startups. So when you're growing, a company, right? This would be the case when the number of customers, number of users is equal to some sort of an initial value times e to the power of b1 times time. So it's about like sign up rates, right? Like we're not talking about active users, but sign up users. So um, Facebook, right, when it grew, it was growing by the day, right? By the month or by the week, doubling every say 6 months, 3 months, 2 months. But then when TikTok comes, right, it's doubling every week, something like that. Initially. But of course you can't double forever. That's why it has to be limited in time. When it's limited in time, that for that growth period, it is exponential growth. But of course, the likes of social media like Facebook, WhatsApp, TikTok, all these people, right? Um, there may be still growth, but you at most take over the whole Earth population, right? How can you grow beyond that, right? So there has to be some tapering off, and you might be growing now at the expense of other uh, social media companies, right? So or not, right? So if you're counting sign up users, then they can sign and then lay dormant. So then they start to compare about active users because that counts more, whatever it is. So for the starting phase, that is quite true. So again, it's going to look something like this. All the curves are going to look exponential. Versus, let me see if there is a decay, right? So if there's a decay, so price increases. So price increases due to inflation. So as time passes, again, right? So price increases due to inflation, some sort of initial value times e to the power of inflation constant times time. So this is price of, can be price index, can be price of a particular good that you are measuring, right? And then you have some initial value, initial price, and e to the power of some sort of growth rate times time. As time passes, the price grows. Price of milk, initially $1 per pack. Then as time passes, 1 year, 2 years, 3 years, 10 decades later, it is $2.50. Right? So uh, it may not sound like a lot, but the unit growth, that's like 250% of the initial price, right? So still very alarming. Okay. Um, depreciation of assets. Depreciation of assets. Asset value. So it can be also appreciation. But then because appreciation of assets, if it grows too rapidly, it's probably not a very it'll be a scary investment, right? So if it grows exponentially, you might want to be very careful with that, right? So depreciation of assets is kind of more common, more natural, more acceptable. We are not very alarmed by it, and it will be something like the worth or the value. The worth of it is um, modeled by some sort of an initial like principal, the purchase price of the asset or something, e to the power of minus b1 against time. Here we will have a decay. We don't call it decay, we call it depreciation, but it means the same. That is that as time passes, initially you have some value, then it starts to decay, all right, towards zero. And of course, if your decay is not rapid, then your B0 should be very, very close to zero, so that your B1, right, is very close to zero. Then the worth is essentially capped at B0 for some period of time. But after that, it starts to halve. Then after that, it starts to halve again, right? So these situations, you will want to use a model like this. And in fact, you can just say B1 because then the value will be negative coming out from the analysis. And then we finally have another description that is, I think, actually much more relevant and easy to understand. And that is the spread of information, spread of rumor, let's say. So the count of people, right? Number of people is hearing that rumor is at first B0, maybe one person, so B0 is 1. Then e to the power of, as time passes, you have the spread rate, right? Then it starts to grow. And this is explosive growth, right? So rumors are or tend to have explosive growth like that. So very, very rapidly spreading rumor will have a very steep, explosive growth. For example, Taylor Swift is coming to Singapore, right? So quietly, a week before, even before government announced it, right? Maybe words leaked out. It didn't happen. I'm just saying, right? So I'm just saying that if words leaked out, there's some rumor that, hey, you know what, Taylor Swift is coming. I heard a big star is coming from US. I just don't know who, right? So word starts to spread. Hey, you know what? Then of course when it goes to Taylor Swift fans, they also connect up pieces of information. Suddenly they realize, oh, it has to be Taylor Swift, right? And so the rumor becomes more real because now it's spreaded by Taylor Swift's fans, and then it how does it spread, right? So 1 is to 4 of your friends. I assume you have 4 friends, more than that, right? Then you say, well, not all 4 friends will spread the word. True. Let's say it drops to 2. So 1 spreads to 2, 2 spreads through social media to 4. I think that's a very conservative number, right? You post it, I think easily more than 2 people will read. And so 2 spreads to 4, 4 to 8, 8 to 60. Initially, you see that the numbers double, and they are very small numbers. But after a while, right? After a while, so 4 to 8, 8 to 16, 16, 32, 64, 128, 256, 512, 1024. It just takes 10 intervals, 10 spreads, 10 clicks, right? 10 people to click, 10 different people to click. Then you reach 1,024 people. And imagine that, after that, when you hit million, it takes 1 more click for every 1 million people, 1 click to reach 2 million people. Right or not? Yeah. So that's why when you grow to certain size, that's explosive in nature. Boom, it goes, like everybody knows, right? So no wonder, right? If some usually dark secrets, when it's leaked out, seems like everyone in the office knows, right? So that's the kind of model we would use. But more importantly, it's very applicable to anything most of the time, anything that is bad. So rumor is bad, right? And virus is bad, right? So virus, the study of spread of virus, epidemiology, right? Would want to use the exponential in order to know the rate of spread. So, for example, as time passes, the number of people reporting sick, right, infected with COVID-19, reporting serious illness, because assuming all the doctors dutifully report such cases back to Ministry of Health, then there is this data there. So as time passes, the data is published, right, and we can all download, and I did initial days, right, to do this study. My model chosen was exponential model because I didn't know whether it is exponential or not, but this is like the worst case nightmare, right? And we want to know whether it's nightmare or just a bad dream by knowing B1, right? B1, if it is positive, right, e to the power B1t, if it is positive and a large number, first of all, if it's positive, then it is positively spreading. Now, this is like 1 is to 2, 2 is to 4. Maybe 1 is to 4, 4 is to 60, that kind of rate. If it is large, then it is spreading wildly. But if this virus, right, is also deadly, that means the morbidity is high. It easily causes death, right? And B1 is large positive number. Let's say from search of past studies and research and medical community, let's say if B1 is larger than 2, then it becomes high, it's classified as highly contagious. I don't know what number is, but suppose there's a cutoff, right? So beyond certain positive number, let's say 2 for now, then it's considered highly contagious. Oh, okay, then you know that the authorities can then plan. Everybody stay at home, quarantine, right? Stay at home and quarantine. No one's to come out at all, and no one's to go to work and whatever. We will uh, uh, confront this virus at whatever cost, right? Because health, life is more important. But if this number is positive, and yet it is a very tiny number, like it's positive but 0.0015, then we know that this virus we haven't seen before, like subsequent new strains of COVID-19, right? So in those cases, are they becoming more contagious? Is B1 for this new virus larger and larger, right? So that means the virus starts to learn how to spread quicker, right? It's got some intelligence, or is it now down to 0.0012? Okay, that means one spreads to 1.0012, something like that. Then, how to count 1.0012%? It will be something like, instead of every increase in t, right, it becomes every increase in uh, 20 units of t or 30 units of t. Like 1 month later, then it spreads to 2 other people, something like that. But by then, the first person who got the virus would have recovered, let's say, right? So it does not seem to be, because this model doesn't take into account the recovery rate. So it only talks about people who are infected or have been infected, right? Even if they are recovered, it's counted. So if it starts to spread to 2 people 1 month later, right, and this first person has recovered, then there's only 1 person to spread further, right? So it becomes not so contagious, and then we can relax the measures. Don't be so drastic at our economic disbenefits, right? So nobody's working, so the GDP will be hit, right? So then the reaction will be appropriate. And if B1 is negative, that means maybe this virus is self-destructing. This virus is not able to adapt to Singapore's heat, so it dies naturally. Yeah, not even a news, right? So don't worry about it. So you see that this B1 is really very important number for us to react to this new thing, right? New virus. So that's why we definitely have to know it. Now, back to my own experience. Actually, in the COVID-19, I actually tried exponential regression and then forget about others. Why? As my first take, that means COVID-19 was new to everyone on earth, right? But there were published data, right, from various countries, including locally Ministry of Health. When so I can download the spread of, that means people reported. So though that's still maybe the tip of the iceberg, right? So not counting those who are infected by having no symptom. But I downloaded those who, serious illness people, and use that as my number of people, and then as time passes. So because those information were dated, right? Why I use exponential is not because I know the study of virus very well. It's because this would be the worst case scenario, the nightmare. So if B1 is a large positive number, then we have a nightmare, right? If B1 is a small positive number, we may be suffering from a bad dream. right? And if V1 is otherwise, then probably don't worry, I can buy more stocks. If other people panic and sell, stock market falls because they don't know what's happening, they don't know exponential modeling, right? And then I know and I realize actually my initial investigation B1 is a small positive number. So it might cause some scare, but actually I know for sure it's not going to be a big deal, right? So then I can capture the unfairly priced low prices of stock markets. So what happens? Well, initially it did fit the exponential model very well. Okay, uh, I look at the p-values and the r-squares and all the quality measures of the model. Does it fit well? Shows that the data fits very well. So it was spreading exponentially in the initial month. Okay, and subsequently it starts to disagree. Subsequently, it was probably 6 months later or something. It starts to disagree more and more with the exponential model. So yes, I can always fit with an exponential model, except the data points will be sometimes floating way on top, sometimes floating way below, like hanging around, drop, like being hung around or being blown up, and just doesn't sit on the exponential curve coming out from the calculations very well. That means it doesn't hug the exponential curve, right? Some points hug it well, the rest don't do very well, right? So that means the quality measure of the fit becomes lower and lower, which means that another model fits it better, which means the virus has mutated. You see, it's telling us a lot of things when you can interpret the coefficients well. And of course, how does that affect me? Well, at least I can anticipate what will be the reaction of the public or even the authorities, right? So since I have no communication with the authorities and they know what to do, so I can then plan for my own thing. But if I am if I'm CEO of a company and I can anticipate government reactions, then based on the innate true nature, all right, of the spread of the virus, then you know uh, I can then plan for the company. In fact, I just share with you, since I'm talking about this experience, another exercise I did when at the start of COVID-19 days. Not only did I use the spread data, that means number of people infected, reportedly infected, to exponentiate against time to fit the data, because that is to tell me how easy, right, the virus is spreading. I also downloaded the morbidity data. I wasn't so much in Singapore, but elsewhere, right, I could download the data, and thanks to the authorities who published the data, right. So I downloaded and tried the exponential model. Of course, exponential will always try to fit. So when I looked at the data, the quality of the fit was not as good as the spread of the virus. So the virus was very spreadable, right? So it easily goes to some other people. Why, I don't know. I'm not a study of the virus, but I do know there's such a pattern. And I know, however, that hey, thankfully, the virus is not so morbid. That means the death of people is not being spread in time. In other words, it's not like one people died, then two people died, then four people, 8 people, then 60, then it's like dying exponentially with time. It may lag behind the spread, so the spread will spread more people first, right? So then it exponentially die, right? The people die off exponentially as time passes. It may be the case. So when I did the fitting, it didn't fit as well because the first fit, the spread model, fitted very well. The quality was very high. The death data, however, was, if you just look at the quality number like adjusted R square and all these, it's okay, pretty strong, right? So gave me a bit of a worry. But if I compare it with the spread model, it wasn't as high in quality. So in other words, the fit wasn't very good. So that gave me some sense that, hey, maybe it wasn't as morbid. That means it's not killing uh, as powerfully as it spreads, something like that. So that gave me a little bit of confidence, right? So that's how I can then react and plan and be more confident about life. That look, it's not so scary, right? Despite the initial fear and panic because of lack of knowledge, right? So with this statistical analysis, I gain more understanding about the nature. In the initial period, way before any talk about vaccine and all that, because all the governments in the world, they were just reacting to situation, right? Firefighting. So that was a good, example, right? And my own personal experience to share with you about the purpose. So even for virus, that has nothing to do with my work, my teaching, my whatnot, right? Has got to do with my life, has got to do with the business of my life, right? My investment, my reaction, right? My planning for the next step, maybe for 6 months down. What should I do? How would the virus evolve? I can imagine, but I cannot start to tell the public and say that this is going to be like this, right? So I can only absorb and use that information for myself because I'm no expert in virus and it's only statistical. But yet, all these will help me gain insight into the situation a lot more. And if, like I said, if I was CEO of a big company, I can plan and make better decisions knowing, yeah, how easy or difficult, right, the virus spreads, whether it will make people uh, die and cause a lot of deaths or not, right? And therefore anticipate how the reactions might be, because clearly scientists will eventually, on the authority side, advise the authorities to do the right thing, right? Okay, so that's what I want to share with you about the examples, a lot of examples, right, for non-linear models. And let me just shift myself back here, right? And next we'll talk about a little bit of the mathematics governing or supporting, right, all the three models, the polynomial, power index, and exponential models. All right, so in what follows, we would try to understand a little bit on the theoretical basis for performing polynomial regression, power index regression, and exponential regression. How does it work, right? Of course, we won't try to numerically calculate them because it's very, very tedious and very, very involved. But fortunately, the whole principle, the thinking behind is really straightforward, right? For the three models. And the idea is very, very simple. We as in statisticians, mathematicians, right? We can invent a new theory, one each, right? To, you know, calculate the various coefficients for polynomial and power index and exponential, right? So we will end up having a number of theories, right? One each. Or we can do what we do best and not have to reinvent the wheels, right? And say that let's try to just use the linear regression somehow. And then by either pre-processing the data to massage the data into something that we can use in linear regression, and then cleverly, right, interpreting the outcome to in the context of the non-linear case, then we can save a lot of problem, right, by trying to invent a new theory that maybe that has a large common uh, portion that is the same as linear regression, right? So so the idea is indeed going to work, and that is that we will actually reuse linear regression. So in the polynomial model case, right? Polynomial model case. Okay. So recall that in this case, y is equal to b0 plus b1x plus b2x squared plus so on and so forth until bkx to the power of k. Now, each of these x squared, x cubed, and all that, they are not new measurements, right? So essentially, you just take the value of x and you square it, and you can produce this reading. And what we do is to treat this as a new variable, x2, x3, and treat this as a new variable, xk, right? So we just use these numbers as if they were measured. So we treat a mathematically derived value. We spend no effort, right, in getting x squared because we already have the measurement of x. So we just take the square of the value, but we treat it as if we measured it like a new variable. So now it looks like it gets transformed into a form where it looks like y is the same y, b0 plus b1 x1 plus b2 x2 plus and so on and so forth plus bk of x of k. Right. So in this case, we would then use the usual. So use linear regression, multiple linear regression, right? And then feeding in the x1, x2, x3 like nobody's business, like as if we actually captured those values. Understand that? Right. So we did one measurement, x only. Okay. Maybe that's the price. So we obtain the price of our product at the retail stores or whatever it is. And that's it. So we get this price, and then we square the price, and then so we actually don't need to measure more things than just x alone, than the price alone. And then we look at our revenue. How is our revenue related to the retail price? Remember the retail price, we are a manufacturer. So by the time our product, maybe it's canned food, canned sardine or whatnot, by the time it's priced at the retail store, the number is like beyond recognition, right? So we maybe sell $1 to our downstream, and the retail store sells at $3.40, right? So something like that. So we just capture that number, x, and then we square it, and then use those square, cube, fourth, fifth, x to the power of k, treat those numbers as independent variables, which is like weird, right? Clearly they are dependent on x. That's why I say calling them independent variables is really like a misnomer, pretty problematic. But we treat them as explanatory variables of our revenue y. Then we run MLR, and the various MLR, they will give us a summary report, which you can sort of look at. The previous video, I went through an example output, right, from Python and the various components. So it's very rich and very informative about the whole model and its quality, like R square, adjusted R square, model tests, variable tests, all the values, right? So we can then extract those values, and the coefficients coming out from that will be our coefficients, right? So we get all the BIs directly from results. Because the function is also called summary function, so output summary report. Right? So then we are done. Very easy. Okay. Then we can quickly move on to the the power index model, right? So the power index model looks at y in the form of b0 times x to the power of b1. Now, in this case, we are unable to just directly plonk the x into linear regression because this is very non-linear. So what we do is to apply ln on both sides. Okay, so well, I'm deriving, so I better use a not so distinct color. And if you ln on the right side, I don't want to write so many steps because the whole video is not about deriving. But if you apply ln on this right side, right, number one, you can use the properties of ln. Ln of the product of two terms, b0 and x to the power b1, these two terms can be split, right, into ln of b0 plus. So ln has this property. For that matter, all logarithms. Ln means logarithm base e, 2.718281828. So ln has this property, all logarithms have this property to convert, in some sense, split the multiplication into plus. So we will have ln of x. And all logarithms have this very attractive property, at least in our case, to bring down the indices, right? Because this index always magnify the data, the base number, right? Because this is like saying use x to times itself b1 number of times. If b1 is 2, then it's squaring. If it's 3, it's cubing. If it's 2.5, then there's a mathematical way to get somewhere between x squared and x cubed. And that is to magnify the number, right? And log has a way to bring down the b1. So we bring down the b1, making this whole number a lot smaller than x to the power b1. So if you look at large number as demon, then b0 times x to the power b1, like a huge monster, right? Logarithm, I like to look at it as a monster slayer, right? It's able to like cut the power index down, right? Split the times which make the number larger. 5 times 4 becomes 20. Make it into ln 5 plus ln 4, which is nice, right? So a lot smaller, a lot tamer in the numbers. And that has got to do with a lot with the ability for computers to calculate more accurately, more stably, and then we get our results more quickly, having more confidence that it is the right result. So what is the big deal with this taking of ln? Now what we do is we treat this as, for example, v. We treat ln x as w. Then it is quite clear, I hope you can see, that it is actually v equals to some constant, because ln of a constant is another constant, right? It doesn't look like b0, but it's another constant, plus another constant times w. But this is basically a linear relationship. It is linear between v and w. They are not linear between y and x, right? But we can look at the v and w space. The v and w space, right, they can be piped into the usual linear, multiple linear regression. We get from the results C0 and C1, right, from output result. That is readily readable, right? Just one function call away, you can get C0 and C1. All right? How to get v and w? The whole vector of y, you take the ln of all the values. The whole vector of x, you take the ln of all the values. So how do we get back b0 and b1? Because what we are after is b0 and b1, not c0 and c1, right? But as you can already see, quite clearly that for b0, ln B0 is C0, right? So B0 is just e to the power of C0. So ln B0 is C0. So this implies B0 is e to the power of C0. And we have directly B1 is equal to C1. So these are all very easy calculations, right? So with this in mind, then we can straight away look at the output and start interpreting. And by the way, as I kept repeating in the sessions 7 and 8 videos, that we are seldom very interested in the analysis of the y-intercept, because it just, in this case, it may have some, because it's non-linear, right? It may have some interesting value in the information, but the very important thing is still B1, right? Yeah, so immediately it is readable from the report. So that's nice. We can just go ahead and directly look at the gradient and say what happens, right? So that's very, very reassuring that we have a very theoretically supported way for us to just take advantage of our MLR knowledge function call in the software library, and our interpretation, which is a learning curve, right? Remember? So the learning curve will be the time to understand the next problem is going to be reduced with our improvement in learning of that technique. Okay, then let's move on. So since power index is so straightforward, then the exponential model. In this model, we have y equals to b0 e to the power of b1 times x, right? Do you see any pattern in the way we should tame the monster here? Exponential is the biggest monster right now, yeah? So it explodes things out, right? And so what you want to do is you take logarithm, correct? So we take logarithm on both sides, and that would mean that we take the ln of b0. There's a times here, right? So we split the ln of e to the power of b1x is going to be itself, because ln is anti-exponential, or exponential is anti-ln. They are inverse function of each other. So the ln of e to the power of b1x exactly is just the index itself. So it's kind of like bring it down, right? Or another way to think about it is it is the ln of e to the power of b1x is b1x times the ln of e. The ln of e is the base itself, right? Ln is base e. So logarithm base e of e is 1, always the case. Logarithm base 10 of 10 is 1. Logarithm base 2 of 2 is also 1. So that term disappears. End up, we have this. You know the trick, right? So we take the ln of vector y and call it, if you like, call it a v. We can, with practice, you just learn to call it, to look at ln of y as a variable by itself. And x is just x. We can copy and paste and call it w. And this is to be set as a linear relationship between v and w, right? So same thing here. So we have kind of like successfully transformed the whole non-linear exponential model into linear form. Process that we call it like linearizing it. So linearizing. So when we linearize, we can obtain a linear relationship between them, at least on paper, in theory. And then we will be able to use the MLR function of the standard library calls. Right. So using MLR again, we get C0 and C1 from output. And we can then interpret the output, right? Now, ln B0 is equal to C0. And so this implies that B0 is equal to e to the power of C0. And then, sorry, put a C0 and C0, so be C1. Okay, and then C1 is just P1. So end up we have shown that actually both ways of both models, right, end up having the same easy conversion in the output result. So we look at output result, we get two numbers, C0 and C1, right? So those numbers end up, the C1 is exactly what we are after, the very important B1 value. And the C0, well, take exponential of it, you will get back B0. So very simple conversion. And then we have so-called solved the model entirely. Finished, done. Because the moment we get B0 and B1, we know the whole model. Bonus, right? Bonus is the output will also contain the adjusted R square, the p-values, right, of the test, and so on. So what we want to know is the model significant or not, right? So we can use the p-values to determine, and then the R square, the adjusted R square. Okay. What do you need to be careful? So careful note. Let's put a careful note there. Okay, note number one, we use the summaries R square, adjusted R square, model p-value, and even variable p-values as rough indicator, right, of the nonlinear model. Okay. Why? Because strictly speaking, R square, adjusted R square, model p-value, variable p-values, they are about the variables v and w. They are about the transformed set of data, right? So no doubt x is not transformed, but yeah, it's about ln y, not y itself. It's about this linearized form, not about the exponential form, not about the power index form. So those values, they are correct for the linearized form, but when we kind of directly use them directly on, oh yeah, the nonlinear model is significant or not significant, we have to use that with a pinch of salt because it may not work in some cases, the borderline cases and all that, right? But by and large, we can use it to approximate. So if the adjusted R square looks good, 0.95, maybe we can discount a bit. Okay, maybe it's not 0.9, maybe it's 0.9, but still not bad, right? So that's why it's good, something like that. And if the p-value is 0.00004, it's very, very significant. And even if it's approximate, maybe in the original exponential model, it's a bit bigger, right? P-value is a bit bigger, but it's probably not as big as to become 20%, thereby saying that the exponential model is not correct, right? So unlikely to be the case. Then also you can have because it's one variable trying to model y, right? X trying to model y, just one measurement trying to model y. You can do a scatter plot, 2D scatter plot, and the shape can be verified visually. So you do have a good note, right, of whether it is true or not, right? So we just use it, right? But caution is they are approximate rough values, huh? So in borderline cases, you want to be very, very careful. Also, if p-value is 1%, right, or 3.4% or 5.2%, and your alpha is 5%, right? So it's like borderline there. It may or may not be significant. Then you want to be careful. Should you then set a bigger alpha just to make it significant? Or should you say, okay, let me do a bigger sample size, right? Let me go back to drawing works, right? Or maybe use some other models, something like that. You just want to be careful and super careful with the interpretation of other parts of the output values. Huh? Just always remember that it's all about the linearized form, not about the original non-linear model. Okay, so just that caution. But other than that, we can then feel free to use the model to do prediction, explanation, and that stuff. Okay, all right. Just one more quick word, right? Number 2 here, perhaps the note here, I can say that if you hear something like some percentage, I just write in symbolic form, percentage increase or decrease in X leads to percentage increase or decrease in Y. All right, so in this case, then you want to use or consider using power index form, because it is the magnitude that gives the subtlety of which model to use. Implies means usually, typically, not the mathematical strict, oh, therefore it's a law, the law of mathematics. No. Okay, so that means if practically you hear that when we increase our prices by 10%, you know what? Our revenue also increases by 10%. Okay, remember it's absolute, not dollar, right? So it's it's percentage, not dollars, relative to the price. Relative to our revenue also increased by 10%. That kind of saying means you should choose the power index model. It tends to fit better. It will be our B1 basically. All right. So this increase will be our B1 essentially. If you talk about 1 unit increase, 1% increase, right? So our B1 will be able to tell you the magnitude of increase in Y when there is 1% increase in X. Okay. Now, let me stress again, maybe sounding a bit repetitive, I know, but this is percentage of. Percentage, there's always a of what? Of the previous X. Okay. Our price was $1. When we increased to $1.10, we noticed that our revenue went from 1 million to 110 million, an increase of 10%. And then subsequently, it's also the same, right? Then you're kind of smelling, sensing the application of power index model. Okay, that's the way we estimate what model is good. Okay, since I would say this, then of course it brings up the question, right? What about exponential? Okay, for this, let me just highlight first, because it's really very helpful, right? I think to have some sort of a cue, right? A hint, a verbal or descriptive hint, signal that, hey, you know what? Signal, power index model, right? What about sort of a verbal cue or hint about exponential, right? So you want to like hear something like unit increase in X. That means some stated units, same unit as X. If X is dollar, then some dollar, sorry, I mean it's $0.1 increase in X, increase in our price, leads to percentage increase. You see, now it's disproportionate, right? In Y. Okay. So notice this here, the unit increase, unit increase leads to percentage increase. So it's like, think of 1 unit increase, can be 2 units, then you divide up. But 1 unit increase, 1 unit, one unit increase, like 10 cents increase, leads to 20% increase in our profits. Just hear that out. 20 cents in 10 cents 10 cents increase in our price leads to 20% increase in our profit, which is wonderful, right? Now, again, remember, percentage has to be percentage of, right? So 20% increase in our percentage of profit. 20% increase in our profit. Of what? Based on what? Based on our previous profit level. So another 10 cent increase, that means now 20 cent increase, leads to, well, it's not going to be 40%, but the previous 20%. So suppose the earlier profit was $10,000. So 20% increase will become $12,000. Then 20% increase of the 20% increase. So it's no longer $14,000, but rather maybe 144, right? So $14,400, more than $14,000. And if you increase some more, it will increase yet even more than the linear estimate. So it becomes exponential in nature. Right. So this means that, or approximately means that, consider exponential model. Okay. And the increase will be reflected by 100 times B1. So whatever B1 you read, you just multiply by 100, that would be the percentage. So for 20% increase, you are going to see a B1 of 0.002, because if you multiply by 100, you get 0.2. Attach a percent to it, that's, oops, I said the wrong thing. That becomes 0.2%. Huh? So it will be, if you multiply by 100, you get 2 and then 20, right? So you should see a B1 of 0.2. All right. And if you multiply by 100, that would be 2 and then 20, right? So you attach a percent to it, then it becomes 20%. So that's the significance of B1, right? Which is a very big multiplier there, the 100. The 100 is derived theoretically with some approximation, right? So if B1 is less than 1. If B1 is greater than 1, then this approximation doesn't work. So this is just to simplify the quick reading. If you see a B1 in the exponential case, right, that is less than 1, then you can do a quick mental multiplication of 100, attach a percent to it, then you see that it is percent increase. That percent increase in X whenever, that percent increase in Y whenever X increases by 1 unit. You just do one more and you get this percent increase over the previous. So if it's a growth percent, then you are basically increasing. But if it's less than 100%, then you are dropping in value, right? Yeah. Okay. So that's the way to quickly think about the interpretation. Okay. In actual data, practical data, the B1s here won't be so wild, right? So they will be numbers in a manageable range, right? So won't be too large. I can't say what is large. It's all contextual, right? Of course, you can have millions of dollars of revenue, billions of dollars of wealth, right, etc., that you are trying to model. But choosing a right unit, end up you will still get back a very tame, small, manageable value for B1. I didn't say that for B0. So if you are doing some sort of wealth management or something, right? And you're using exponential model, your B0, the initial multiplier here, could be large, right? Could be if you have billionaires in your customer profile, then it might be several $billion. So this could be large to bring up the level, and then your B1 doesn't have to be a large number. So it is about growth rate or decay rate, right? Or learning rate or whatever rate you're talking about. So basically, the rate cannot be very huge. If huge, then it's something different in nature, right? So we're talking about all these similar field as in learning rate, organic growth rate, spread rate, right? All these things. So the numbers tend to be manageable, and small change in that rate, because it's simultaneously carried out by a lot of entities, a lot of multipliers, it'll be exponential in nature. All right, let's move on to the last segment of this video, which is to discuss about the logistic regression model. Logistic regression model is much more, or rather maybe a bit more complicated in terms of the mathematical theoretical support. That means the basis on which we try to find the coefficients, right, to complete the model. However, we need to still learn it, right? Because we encounter this a lot. So what is basically logistic regression? Why can't we just directly use linear regression? Right. So in this case, the y values, the outcomes, right, consist of either ones or zeros. Okay. Maybe it is success, right? Maybe it is positive, tested positive, right? Like COVID-19 tested positive, and then failure, right? No success, not success, or failure. COVID-19 test kit tested negative, that kind of thing, right? Or you are not positively infected, or are you going to become bankrupt? Yes, you are bankrupt. No, you are not bankrupt. Typically bad things. Sometimes good things. Okay, sometimes good things. Did you score A plus or not? Did you pass the marathon qualifying round or not? And so it can be success, it can be failure. In the statistical sense, that means the thing that we are trying to observe. If we see that, that is success. Okay. Did this student cheat? Okay. Did this submitted essay, was it a cheated piece of work? So that is, of course, a bad thing. If we found one, then that is success, right? So then we record y equals to 1. Otherwise, we record y equals to 0. So example, for a class of 30 students, I received 30 reports, essays. Look at them, right? By right, I should get 30 zeros. That means no cheating, right? So no cheating. But if I read one of them, teachers always have that sense, right? Hey, this looks a little bit weird. I have seen that somewhere, right? Is it lifted from some famous results or reports or another student's work or something? I've seen this before. Where did I see it? Okay, some suspicion, right? So maybe after confirmation, yes, right? So then it's a 1. So that's a record of the response variable. And the explanatory variables, the usuals, right? For example, the length of the essay, the number of verbs used, nouns used, all these that are very evidential in the content, right? So all these are the x1, x2, x3s. So based on that, if we do a regression, let's say we just have one variable, because then I can draw a diagram to show, right? If we did regression, then what happens? Right? So in this case, if we use normal MLR directly, right, feeding the y values directly inside, then notice that we will get 2D diagram, no doubt. Right? So let's say time of submission. So if time of submission before deadline is very short, so last minute submitted, very likely cheating because student, okay, it's probably not a fair conclusion, but talking about after that we do other confirmation, right? So suppose X is the timing, right, of submission. Uh, suppose in the past we recorded that very late submission, right? Very late, right? So this is the deadline. Deadline is somewhere here, right? So this is like time of submission. All right, and y is either you cheat or didn't cheat. So suppose we spend a lot of time looking at past results. Time of submission can be varying, right? Can be before the deadline. Let's use another variable. So before the deadline, well, before the deadline, so no cheating. Draw wrongly. So way before the deadline, no cheating, right? Way before the deadline, no cheating. And people will submit, right? All these. So there'll be a blob here. And then there will be a few who submitted just before the deadline. After checking, no cheating. And then those who cheat, a few of them will occur here, like 5 minutes before deadline, right, or something like that. Okay, so this 1 here means cheating, 0 means no cheating, right? And we will see this. We will not see anything in between right now because it's undefined in our experimental measurement context. Then what we do is we will have a linear regression like this. And then we can start to say, let's fit in the values of X, right? So for the time of submission of 5 hours before deadline, we submit, the model predicts Y equals to 0.35. Oops, what is that? No idea. 0.32, 0.55. Problematic, isn't it? Yeah, so we cannot understand. So cannot interpret at all predicted Y's. Example 0.34. It's not probability, because we are saying the Y unit is didn't submit and submit. There's no such thing as 0.5 means half the chance. What do you mean chance? These are all recorded historical facts, right? So there's no chance, right? So it's not probability. And worse is, suppose we are talking about 5 days before deadline. So the predicted Y can be negative, which is also problematic, right? So definitely not probability, right? Or the predicted Y, if we say, well, what if we allow for grace period? The person submitted 5 hours after the deadline. So the status of cheating is Y equals to 3.52. Don't know what it means, right? Yeah. So then we have a big issue with the linear model. Okay. And so what we want to do is to be able to establish some sort of probabilistic statement. Okay. So to do that, we need to have measured probabilities. In other words, for 5 hours before submission, we better get like 100 such students. Just example first, right? You already understand it's absurd, right? But 5 hours before, we get 100 students submit, then see who cheats. Then 4 hours before, we get 100 students who submit, then we count how many cheats, and let's say there are 2 people cheating, 2 out of 100, that's 2% for 4 hours. Then we can estimate the probability. And even so, it's very ridiculously crude, right? So we just probably get 1 decimal place. And that's very, very unrefined. So what we want to do is to be able to get some sort of y equals to 1, right, and y equals to 0, to be able to perhaps, right, perhaps that's our dream, that we want to get some sort of a curve, right? So we want to get some sort of a more continuous nature, and whether it's a strict S, a hard S with a very abrupt, almost vertical change in the S direction, or a smoother one should be then driven by data. So if data is more diffused, right, whether students submits early or late, there seems to be equal proportion of people cheating, that kind of thing, then it may be a very stretched out S because you can't tell, right? But if it is very distinct, then the S becomes more strictly defined. It's almost like a cliff, almost, but it's still increasing just at a much more steeper gradient. So whatever it is, it should be driven by data to describe this. And we ask, can we have such a model? Right. So answer is yes, right? So yes. So answer is that we will have such a model to go from minus infinity to infinity, right? The function is actually called the sigmoid function, right? And let's just call it z. Is equal to 1 over 1 plus e to the minus z. Or in this case, x, I think better, just to go along with my x-axis. So y is the sigmoid, and the sigmoid of x is going to be this. So why this? No reason. Okay, to be honest with you, we just play around, or rather statisticians, mathematicians play around with functions. They come up with this. Why this? This is nice because it takes in any value of x, even from minus infinity to infinity. You can throw me any interval, right? Any number, large or small, I don't care. And this function will produce an S-curve, right? Rising from 0 at minus infinity to 1 at infinity. Only touching 1. And it's always rising. So that's the nice part. There's no staircase curve, which is unwelcomed in mathematics because it cannot be differentiated. You have to do it part by part. You have to analyze it and then be careful of the abrupt change in the staircase height and all that. So a smooth S-shaped curve is very much welcome, right? So because of that, we adopted it. And then we see whether this model makes sense or not in real life. If it does, then good. Then we use it. And if it doesn't, then we look for another model again. So the regression that we want is going to be basically doing this, right? So we're going to call the where's our model? Okay, the log of the probability of success over 1 minus the probability of success is equal to our b0 plus b1 x1. If you have only one variable, you can stop there, but you can also increase, right? Just like any multiple linear regression. Then you can have k variables, and we call this the logit. L-O-G, log of it. What is it? It is the p over 1 minus p, where p equals to success probability. The real probability, which we want to know but cannot know, right? Probability. It's a bit like the population mean probability, but we don't call it the population mean because probability itself, we don't think of it as having a population. But it's like the true probability of success. That means in my cheating case, what is the actual real probability that a student, a randomly picked student, submission will cheat, okay, by copying or using GenAI or whatever it is, right? So success probability that I found a cheating case based on evidence x1, x2, x3, x8, x8. So that is going to be giving us the essence, right, of building up the logistic regression. And when we are done with this, so in other words, we will regress or perform logistic regression of the logic against the x1 to xk. So these are the variables that we will collect. For example, time of submission, right? So that's evidence I can collect. Then I will get the value y equals to 1 or y equals to 0 and put it inside. Okay, so once we can, so the function, imagine the Python function, right, will take in the y values and the x1, correct, the n samples of x1 to xk, and then number crunch it, and that part is a little bit more involved, right? So then out comes the answers. What are the answers? The answers will be the b0, b1, bk. So once we have that, we will then be able to produce these probabilities. So what is the usage of it? The usage of it is going to be the probability of y equals to 1, right? Given x is going to be 1 over 1 plus e to the power of minus the logit. Right, so in other words, minus the b0 plus b1 x1 plus all the way bkxk. So the logit itself. Okay, so once we have the b0 to bk's, we evaluate it against our evidence gathered. For example, next exercise submission, right? I obtain another student submission, and the time of submission is 5 minutes before deadline. So I plug in 5 minutes before deadline into x1, whether it's absolute time or time before and after deadline, up to me, right? To calculate. So I standardize the measurement, and I would then be able to compute the logit, right? So that means the whole thing. I can backwards evaluate p, of course, because I can always use exponential, right? So e to the power of the ln of this will give me p over 1 minus p. So e to the power of this whole thing will give me the p over 1 minus p, and I can reverse out the p, the probability, success probability, right? So then I can know, right, if the student has what probability of cheating. Right, so if I plug in here, then you will see why we can then estimate the probability of the student cheating given that he or she submitted 5 minutes before the deadline. Okay? And of course, the probability of not cheating is just 1 minus the probability of cheating. So far, so good. Okay, and what we can, of course, calculate is that if we call this equal to y, okay, then let me insulate the derivation here. If I raise both sides by e to the power of ln of p over 1 minus p, I will just get back p over 1 minus p. Right? And the right side, I will get e to the power of y. And if you multiply, right, both sides, then we get p is equal to, I multiply out, e to the power of y minus e to the power of y times p. And I can gather the terms so that it is 1 plus e to the power y equals to e to the power y, right? And now I can reverse out the probability of p is equal to e to the power of y. Remember, y is the whole thing here, b0 plus b1 x1 until bk xk. So e to the power y over 1 plus e to the power y. But that looks different from this, right? Fret not, because they are exactly the same thing. Because y is equal to this term inside. And if I were to multiply by this positive term, e to the minus y over e to the minus y, which I can, isn't it? Because it's just 1. Then the e to the minus y and e to the y, they cancel out, right? So I will get a term of 1 in the numerator. And e to the minus y times 1 is e to the minus y. E to the y times e to the minus y is 1. So end up, I will get 1 plus e to the minus y. Recall that y is just this long chain of linear terms, right? So that's the reason why. So this is actually our p as well. So in case I wasn't very clear. Now the p is just a short form, right? So it's like the probability of getting a success given the observation y, like this. Okay, so far so good. And what I like to do is to just do a very broad base, narration or description of how to get the b0s to bk. And the idea is to use minimization of errors, okay, minimization of errors, by first observing that when we have, okay, so when we have a set of observations x, we can have x1, x2, x3 until, so we can call it a vector x, but I'll just use x, right? So it's just for simplicity. So in this case, if we have p of y I given the observation of x, so the ith observation, right? I is going from 1 to the sample size n. Okay. So if the ith observation, I observe 5 minutes before deadline, 5 minutes, 10 minutes after deadline, 8 hours before deadline, right, and all that, the probability is going to be given by the success probability. Let's just call it pi, right? So same thing here. This is p. Let's just call it pi, just so that it is different from the p. This is very confusing. So pi to the power of yi. Remember, yi is either 0 or 1. So this term is going to be either 0 or pi itself. Okay, and then you have the fail probability. That means didn't cheat. That's 1 minus pi raised to the power of 1 minus yi. And that makes sense because yi is either 0 or 1. So we are taking advantage of the 0, 1 nature. It will not be a negative term because yi will either be 0 or 1. Guaranteed, right? Because we are going to write that down in the data. Right? So remember that yi is equal to 0 or 1. And pi is a number from 0 to 1. Right, so pi is a probability, is a number between 0 to 1. Right, so just remember that. Huh? So that 1 minus pi is never going to be negative. Okay, so that is our chance of observing one instance, one sample. But remember that we obtained all the n observations, right? So I have 30 students, so my sample size could be 30. Actually, that's my population already. But I'm trying to say that, hey, you know what? In the whole university, using my class of 30 students as a sample, what's the probability of cheating, right? Something like that. So then my population is the whole university of students. And we want to say that I observe all the n students, n samples, cheating or no cheating status simultaneously. So this gives rise to this idea of likelihood function. And what is that? The idea of likelihood function, let's just call it L. L of the B zeros and B i's, right? So the L of the beta values, beta 0, beta 1, beta 2, beta 3, all the values. So let's call that a vector. So the likelihood of observing all the n simultaneously acquired yi and xi values, right? That's going to be the joint probability. That means I observe all the n sets of samples simultaneously. So what's the chance of observing sample 1, observing sample 2, observing sample 3? So observing sample n simultaneously. So that's the end probability, right? So assuming independence, then if you forgot independence, then the probability of A and B is equal to P of A times P of B, right? If we know that A and B are independent. So assuming all the students cheating, they are independent. They don't collude to cheat together. That's what we are assuming. Actually, that may be a bit too good to be, right? Sometimes they do collude. But assuming that's the case, then what we are trying to say is that it would be the product of all the probability of yi given xi from I equals to 1 to n. Correct? We times them together. So keep multiplying the chance of observing. This is all theoretical. We don't know the probability, at least not yet, because we're trying to derive the beta 1, beta 2 in place of the 1, 2, 3, 4, B1, B2. So you try to multiply them together. And essentially, that's just saying that it is going to be the product of all the, we use the big pi notation to talk about product, but I just use product of all the 1 over 1 plus e to the power of negative x vector transpose times the beta vector. Right, so since I'm using vector now, so this will be a vector. And yi is a value, either 0 or 1. And raised to the power of yi. Okay. Then 1 minus the whole thing again. 1 minus the 1 over 1 plus e to the power of minus x I transpose beta. Right, and then raised to the power of 1 minus yi. Well, just assume it works, right? So for all of, so this is quite a lot of words to write. So sometimes we just say pi, big pi, big pi, I equals 1 to n, this whole term. Anyways, is to say that we want to multiply all the probabilities together. This is just to get the math correct. And then I'm just going to talk now. So and then we want to do some sort of loss function. That means what's the error? What's the error? So in AI terms, it's called loss function. But what's the error when we try to change beta? So in other words, we want to find the derivative of the likelihood function when we change beta. So we want to like modify beta, because when beta, remember, it's a vector, so it consists of b0, b1, b2, b3, b4. When this beta vector has some values like 0, 1, 2, 3, 4, 5, this may make the likelihood function equals to 10. But why must it be 10? Can we make it smaller? All right. We want to make this likelihood function smaller if we can tune the beta. Or we can tune the beta in such a way that we make it higher. What does it mean by making L of beta smaller or larger? And that's to say that the likelihood, right, of the event happening, which is cheating, is higher or lower. And that is our sense of trying to change the beta, right, to make it larger or to make it smaller. And in other words, that set, that combination of beta will make this whole likelihood more or less. And we want it more. We want it to be more likely. That means we have already selected the sigmoid function. So this is fixed. We want this sigmoid function to have a high likelihood of matching to the data that we have seen. This is matching the ones and zeros of the yi's and the xi's that we have seen, not whether the student cheat or not. So we are going to tune the beta, some sort of a tuning knob. We tune it, the L of beta will indicate a value that increases. That means our choice of sigmoid and the set of beta makes it such that, this function now is able to very likely to describe back the yi's and the xi's that we have already seen, right? Because we do feed those data into the likelihood function. So we feed it in, and this function, this likelihood function, gives us a value, right? And this value, we want to make it as large as possible because we can change the beta. And changing the beta to make the function of beta higher is definitely, right, the skill for calculus derivative. Set it to 0, right? So we just take the derivative of L of beta, right? Set it to 0, solve for beta, then we get it. And once we get beta vector, we are getting B0, B1, B1, B2 to BK, right? Then we are done. Remember, that's our goal, right? Mathematically speaking, that's what we want to do. But when the software folks try to implement this, there is some problem, right? So numerically unstable, right? Because the yi's are either zeros or ones. So 1 minus y also zeros or ones, and you are multiplying them. So in case one of it is 0.00072, then you times 0.0095, you're going to get tinier number. So when n is 4 or 5, you're already getting like 20 zeros in front. And remember, we have a very strong motivation to get large sample size, right or not, right? Central limit theorem and all that. So to get large sample size, which will mean that if most of it are 0, like in our case, right, most students don't cheat. So the yi's tend to be having a lot of zeros. And then we will end up getting 0.00, maybe even hundreds of zeros. Even in today's 64-bit computing, it's going to cause a problem. So very, what we call, unstable. Furthermore, remember, we're going to take a derivative, right, dy dx. So d of L over d of beta. We're going to do that and set it to 0. We're not going to do that here, so don't worry. But the idea is we have to continue that derivation, right? And it's very tough. This is a very tough function. Even with good mathematics, it's just very confusing, right? So we were wondering, is there a better way, all right? Is there a sort of not easier, but maybe a better way? And yes, answer is the log likelihood. You might have heard of it when you are reading related literatures about logistic regression, log likelihood function. So again, let me stress that actually we are okay with this, except there is some sort of a technical difficulty. So taking the derivative is tough, numerically not stable, and those are real problems, and we don't want to get some calculated results that are having some sort of caution. Wait, this is heavily truncated, you don't want to rely on this. Then what's the point, right? So we want something that is, in some sense, far more superior in calculation quality. and that is to take the log of this, right? So if we take the log of this, let's call it the log of beta, which is the log or ln, that's fine, of L of beta, right? And if you do that, then the log will have its demon slaying power, right? To deal with the very evils of this demon, right? Which is that you have the indices, they'll be pulled down to the ground. There will be products, the times will be converted to pluses. So end up, we're going to have the so-called sum of all, and I think you should understand summation, of all the samples from 1 to n, right? The y of the first sample, second sample, and so on, times the log, and treat the log as ln, no problem. The base is not so important, right? Of the probability of observing the ith sample plus 1 minus yi, because this term comes to the ground now, of the log of 1 minus the probability of not observing, or rather of observing yi. And so 1 minus becomes not observing, like this. Now, you don't have to really worry about this one, but I'm just saying that in the guts and intestines of those functions that are implementing or helping you to find the B0, B1, B2 to Bk, in other words, to find the beta vector, they do have to deal with this. And the reason why they deal with this rather than this is that this is a lot tamer, right? Thanks to the log, the demon slayer, they brought down the yi's from the power index to just a multiple, right? And yi's are ones and zeros, so they either make the term appear or disappear. When yi is 1, this appears, and this disappears completely. When yi is 0, this disappears completely, and this term is actually left with just log of 1 minus pi I. Can you see that? All right, so now the terms are a lot easier, and you're just adding up either one of the terms in each of the I equals to 1, 2, 3, 4, 5. So a lot easier, right? Because of the log. And so we will now take the derivative of this, right, and want to maximize. So maximize L of beta, the log likelihood function, by setting the L of beta derivative to 0, right? And then solving for beta vector, then we get the bunch of B0, B1, B2, and then we are done. Okay. Only thing is, are we solving for the right beta or not, right? Yeah, so don't worry. All right, so because log function also has this nice property of what is known as the strictly increasing function, right? So it is not only demon slaying, but it preserves the order. So if you are a billionaire, after log, you're still richer than a millionaire. So if you take log of billionaire and millionaire, billionaire might be 6, right? Having a log value of 6. Millionaire will have the value of 3. A billionaire will be 9, for example, because 9 zeros behind. So billionaire will be having a value of 9. Millionaire will have a value of 6. Okay, billionaire can still laugh at the millionaire. I'm 9 and you are 6, right? So it preserves the order, and therefore, if you're solving for beta that maximizes the logged function, the simple function, that beta also at the same time maximizes the original product function, the unlogged function. So then that way we are assured, thanks to mathematical analysis and assurance, and we are assured that we are solving for the right beta. Okay, and we are going to have a numerically stable function to deal with, to take calculus of, and we can take calculus of this, derivative of this, much more readily. And once we do that, calculus can only make this somewhat easier than then make it more complicated. So after that, it is numerically stable. We can find the beta, and we don't have to issue a warning sign and say, wait, those weights are, those beta, those B values, they're not very stable, so use with caution. We don't have to do that. Because if you do that all the time, then what's the purpose of getting this model, right? So we might as well do something else. So all you need to know about then, after understanding this broad-based discussion, is that, well, you just need to treat the function in Python or R as a black box, right? So you just feed in the ones and zeros, the y values, they are ones and zeros, and the function will understand it properly by deploying sigmoid function, right? And you will be able to number crunch the y equals to ones and zeros properly without ending up with this rather bizarre situation, okay? So let's just do a final quick example to to illustrate how we might end up using this model. Okay, and I want to extract more land from previously excluded area. Okay, just to give my example. So you see, it's going to be a quick one, right? So we were talking about cheating, right? So let's say that I have three variables. X1 is about maybe use of very rare vocabulary. So X1 equals to use of rare vocabulary. Okay. Rare will be like a set of words extracted from dictionary that we all think is rare relative to this context of the essay. X2 could be the average sentence length. All right. So if the average sentence length is abnormal, right, like very long, very short, right, so we can then say that, hey, maybe that's the thing. Text similarity score, right? So X3 can be similarity score. This score number is very well known these days, right? So we will do cosine similarity or whatnot, so it's very easy to just do a function call and be able to get that. And let's say all these numbers, they are between 0 to 1, all right? We standardize their values. They are all scores. So instead of saying 0 to 100, we just divide them to make them weights, right? Something like that. And we will then have a y that is 1 is cheating, 0 is not. So now suppose that I receive a submission, right? And then I use the past data, all the submissions, all the past data that have been verified to be cheating, not cheating, because they are like several years, right? And they have been very carefully validated to see if they're cheating, not cheating. Okay, maybe the student already graduated, but then we discovered, all right, so it doesn't matter. We use that as our feed forward, okay, data analytics. So after number crunching, suppose we get the model y, rather the logit, logit equals to -2, right? Plus 3x1 plus 1.5x2 plus 4x3. Now you see why we may want to have the x1 to 3 being standardized to between 0 to 1, just to make the numbers more manageable. Otherwise, it may be large or very small or whatnot. And let's further assume that from actual measurements of the students' submitted essays or whatnot, right, we get x1 equals to 0.8. So very high usage of rare verbs. Okay, that's okay. That's one signal, but may not be sufficient, right? Then we look at the sentence length, right? On average of the 200 sentences on average, right? The sentences tend to be short, right? I am happy, right? The sun is bright, and the day is bright, and all that stuff. And X3, the similarity score, right? We can use Turnitin or some textual comparisons. We get example 0.9. So now we plug into our logit, right? To calculate, where am I here? Okay, we calculate the logit, and then we plug in the logit here to get the probability. So this is what we are after to make a decision of this case. So if we plug in, I don't have space, but probably I use another color to indicate. Okay, so we plug in to get a Z, not a Z, the logit. So we get a logit of, okay, so if you do the math, I will not extend the expression here, right? Minus 2 plus 3 times 0.8 plus 1.5 times 0.2 plus 4 times 0.9. Okay, so I hope you can do that. We should get 4.3. Did you manage to get 4.3? And if you did, then we don't want to stop at logit because we want to make decision. We want to make decision as in, did this submitted student's essay, did it cheat, right? With these evidence here, 0.8, 0.2, 0.9, right? So you get the logit and we're not done. So this is to be plugged into the probability of success. Success means cheating. So probability of cheating is 1 over 1 plus e to the minus 4.3, right? So the probability of cheating, we use pi here, equals to 1 over 1 plus e to the power minus 4.3 is equal to 0. I get 9866. 0.9866, that's almost 1 already, right? Okay, so 0.9866, if we have a cut off, right? So there's always a cut off. If it is a software, then you compare it with some preset cutoff, right? Greater than 0.75, greater than 0.8, in this case, very much greater, then we flag it, potential cheating, right? So to be considered by a teacher. So there you have, right, sort of the inner thinking, the algorithm towards automated cheating detector. But of course, I gloss over a lot of details. Even if this is very detailed, I still didn't talk about all these. These are also very technical in some ways, right? Sentence length can be easily calculated. Vocab can be identified from a identified rare vocab list. The similarity score, yes, it's easy these days to calculate, right? But the algorithm behind is also quite not so obvious. Let's put it that way, right? But all in all, these are all readily accessible functions, and then you can then do that and then produce a probability of success, probability of cheating. Okay. Now, of course, this is wide. This has wide applications. Usually, in when the success is also bad thing, right? So, because we want to avoid trouble, we want to avoid disaster, we want to avoid damages, right? So, talking about damages, you talk about claims, insurance. That means what's the likelihood that this person will make a claim when the insurance company insures this person, right? So this person has this, right? This illness, that duration of illness or whatever it is, right? So all the evidence and what's the model's probability that this is a fraudulent claim, right? So again, detection of fraud can apply to many areas, not just insurance frauds, but also accounting frauds, right? of course, cheating cases, and many other situations when it is usually, I'm not saying it only applies to bad cases, but usually when the consequence is a bad outcome, the success is a bad thing in our society, and perhaps it's also an unwelcome consequence. For example, what's the probability that this typhoon hurricane will cause huge damages, loss of lives? No, big event. So that's success, right? Unfortunately, the success means huge damages and loss of lives. How huge we are not quantifying. We're just saying what's the probability that this typhoon will land, right? Therefore causing big problems. So that is also another thing. And if the probability, say, is above certain cutoff, conservatively, let's say it's above 40%, then we issue public warning, right? So again, many cases, we can make a decision and call to action. After the cutoff probability, we say call to action. Let's do something to avoid the damage, reduce the impact, right? Or then avoid life losses altogether, something like that, right? So very useful in terms of applicability. So that's why I really wanted to spend some time to go through the intestines and guts a little bit more, so that we don't just gloss over and say, oh, call a function and then you get the coefficients and that's it. But I want to like really go through the examples, and even however squeeze it is, I want to like go through and talk about it, right? And then make sure you can understand it and apply it in your own context and experience. With that, I thank you very much for your attention, and that's all for this video. See you in other subsequent videos.